All right, we're going to take a closer look at the geometry of this double slit interference pattern. If you remember what we saw when you take a light beam, so here's supposed to be like a laser beam coming in from the left here, and the laser beam passes through two openings. So you can see there's an opening here and an opening here. So I'm just going to bold this in to make it a little bit easier to see. Here's the central barrier, and then here is the bottom barrier. So there's these two openings. And what you see when you shoot the laser beam in is that you get this pattern of bright spots in much more than two spots. So these kind of continue out away from the center here. So if you remember, in the center, even though you're right behind the central barrier, the reason it's bright there is there's a path difference of 0 at that point. Okay, so that's why it's particularly bright at that point. So we'll say path difference, I'll say delta path equals 0 wavelengths at that point, right? Now up here, you just count to get to the next dark spot and bright spot. So where it's dark, here the path difference would be half a wavelength. Here we must be back where the path difference then is 1 wavelength. So I'll put delta path equals 1 wavelength when you're up here. Okay, so if we take a look at what that really is saying, the meaning of delta path is 1 wavelength, it means that a wave from the bottom opening has had to go exactly 1 wavelength farther than the wave from the top opening. Okay, so a little game that we can play. We'll do a little bit of geometry to try to learn something about this. If you take that top path and kind of swing it down to the bottom one, you can see there's this little discrepancy between the bottom path and the top one. In other words, the top one is a little shorter than the bottom one. This extra distance that is here is the path difference. Right, so I'll kind of label that on here. So this distance is going to be really important. This is the delta path. This little bit of extra length right here, that's how much farther the bottom one had to go from the top one. Now if you want, here we've played a little bit of a game. It's a little bit of an approximation, because if you were to swing this line down into that one, it would kind of like sweep out like an arc, as opposed to making like a straight line like this. The idea is that, as you saw in the pattern, everything's so tight together that this difference in the path length is so tiny compared to these total lengths that it's a reasonable approximation that you can get away with by sort of swinging this down and pretending that this was a straight line. So what you do is you construct a perpendicular to this line, kind of at that place, and then this, again, this extra distance here is the path difference. And so what we're going to do is work out the geometry for this. Okay, so we've got a few parameters kind of set up here. There's this distance that's called L, that's from the openings to the screen, and there's a distance called theta, that is, or an angle called theta, that's the angle that you have to look up to in order to see the first spot. Okay, so theta just tells you what angle do I have to look up at until I get to a given spot. Okay, and we're going to fixate on the first one. Okay, so this path difference, if you're going to see constructive interference, this path difference, this delta path, needs to be an integer multiple of wavelengths. Okay, equals n lambda. So for instance, at this first point, it's going to be 1 wavelength. So we'll say it's 1 lambda for this first spot. Okay. What we can do is, if you look at this pattern, we have this distance here called L, this distance x that pertains to how far you need to move up to get to the next bright spot. So we basically have this big triangle here, where this angle is called theta, that's right here. Right. This line that we've constructed is perpendicular to this one. Okay, so that line is perpendicular to this one. Right? And what we're doing is, if we find the angle between this slanted line and the vertical, that's got to be the same as the angle between this slanted line and the horizontal. Okay? So what that means then is this little bitty angle here, which I've kind of blown up the picture here, if this angle is called theta, then this angle here, so here's theta in the little picture, or in this part of the picture, that's the same as this theta in the triangle in this part of the picture. Now the reason I'm fixating on that is we need to find the length, this little extra length on this side of the triangle. We need to find what that is because that is the path difference. Well, you can see that we have a little right triangle here. And if we know this side D and this is theta, that this opposite side from the angle that we know needs to be D sine theta. Okay? So what we have just learned then is for this situation, the distance, the angle that we go out to get to the first spot is related to the wavelength and the spacing here by this relationship, D sine theta equals lambda. So this would be like, say, for the first spot, for the first bright spot. And so if you want to find any bright spot, it's going to be D sine theta equals n lambda for any bright spot, where n is 0, 1, 2, 3. So this is for any bright spot. Right, including the central one. If n equals 0, you're here, your angle here would be 0 degrees. So this equation is actually also true for that point. Now an easy way to get this angle is to look at how far apart the spot, the bright spots are in this long length L. These are easily observable in the lab, where this tiny thing, the distance between the slits, let's say, tends to be less easy to observe. And so what we want to do is relate things to things that are easy to observe in the lab. Well, so this angle theta, you can see that this theta, we know the opposite side and the adjacent side. So the tangent of this angle is going to be x over L. So these two relationships will get you pretty much everything that you would want to know about the double slit pattern. It lets you know the angle that you have to look out to in order to see the spot, and you can turn that angle into a position to know how far out you need to go to reach this. Okay, so a couple little features of this. What they like to ask, say on the Physics 2 exam, I'll give an example, is for instance, if you bring the openings closer together. So let's look at a couple cases. If we bring the slits closer together, what that would mean is that D decreases. All right. Well, we can see what the effects are of bringing those slits closer together if we just look at this relationship here. So if you say, well, D sine theta equals n lambda, well, what's going to happen is if D goes down, right, and you leave the wavelength alone, that means sine theta needs to go up. So what that means is if sine theta goes up, the spots are going to spread farther apart because you'd be having an angle that has a greater value of its sine, which is opposite over adjacent. So the opposite side here would grow and grow and grow. So what that would mean is, therefore, you could see that, well, the spots would spread out. Sine theta goes up, so spots would spread out. So you get this interesting behavior that the closer you bring the two openings together, the more you actually fan the pattern out. So that's something that they tend to ask you quite a bit about. Likewise, you can see things like if you were to only, say, reduce the wavelength, right? Notice, suppose we did that. Suppose we changed from a red laser to a blue laser. If you reduce the wavelength, if that's the only thing that you actively change, well, then you would have to reduce this side of the equation too, which means that your angle that the light goes out to, the sine of the angle, would have to come down. So if you reduce this, you must also reduce this. So reducing the wavelength would actually squeeze the spots together. So a pattern with purple light or blue light would be squished together more than a pattern with red light. So this introduction to the double slit pattern, this relationship really relates the angle to the wavelength and the slit spacing, and you can find the angle by looking at a couple easily measurable things in your experimental setup. So that is the double slit pattern. This relationship finds the bright spots.